I knew. Oh, oh my god. Oh,
All right, so okay, so it looks like it's working now. Because I have to change my configuration again, so it's taking a little bit of time. I think my mic is still clipping. At least it's showing that it's clipping. I think it's doing better now. Okay. All right, so there we go. Well, I think we are ready to start the class. I know the screen looks kind of cluttered right now to you because I'm using the smaller screen again, because I can't go to use my 4K screen um, right now. All right, so I'm keeping an eye on the text channel. All right, the YouTube is private. I don't think so. Let me double check. I thought I changed it. Oh, it is. Okay, never mind. All right, so it should not be private anymore. Give it a try. Okay, so I'm gonna type here. Give YouTube a try again. All right. I know it's going, and from what I can see, privacy is now set to public, and I can see people viewing it, I think. All right, cool. So I'm going to close that window because I just don't have enough real estate for on this particular screen. I'm using a laptop. It doesn't really matter whether it's a laptop or not. It's just a 1080p standard um, resolution. It's pretty hard to keep Discord up, OBS up, and also the browser that I want to show to be up. It sounds a little weird. Okay, let me check. Alright, so this may fix it. Give me a second here. Alright, so now it should sound better because what I did was I just disconnected the desktop audio because it was piping my mic output to both the desktop audio and also the mic input. So now it should be fine um, on YouTube. All right, cool. All right, so this is a preview of what we are going to talk about today. We have already talked about the g function that maps from a n by n space into n, and it's a bijective function, which means there's going to be an inverse function, and that's what we'll be talking about today is the inverse function. And we possibly may get into relations, which is the next topic after Aleph No. So that's the plan for today. And let me go ahead and turn on my tablet. And hopefully it is going to show. Yep, okay, so it looks like it's working. All right, so it has not refreshed because I'm already. Okay, there we go. So today we're going to continue with this specific topic is, if I just have a natural number, how do I find the coordinate corresponding to that natural number? So before I go any further, I'm going to switch back to the diagram that we have earlier. So the question is, if I just give you, let's say, 12 here, how do I know 12 is corresponding to the coordinate of 2, 2? So given the natural number, using the way that we assign natural numbers to each pixel, how do we find out the coordinate of the pixel? So I just want to make sure that we understand what we are about to do. Are there any questions about what G inversed is supposed to do? All right, I'm not seeing any questions in the text channel, so I will write this anyway. So G inverse is a function, but the way it maps is it maps from n back to n Cartesian product with n. Yeah, I know I write the two n's slightly differently, but I think you guys got the gist of it. Yes. So Aman is correct, except in this case, I'm using the notation of G inversed because it really is an inverse function corresponding to the original function, which I forgot to put extra parentheses around because G is supposed to take only one single parameter, which turns out to be a two-tuple as the single parameter. And in this case, G inversed is supposed to take a single natural number, and it should give us, x and y. All right, so I'm not seeing any new questions in the text channel, and I'm going to continue, to explain, how, what is the process of, discovering this particular G inverse function. I believe my voice is still clipping a little bit. Not by much. Okay, so I'm going to keep it the way it is right now. I just have to speak a little softly. That's all. Okay, no problem. All right, so now I'm going to talk about the process of how we can discover the function. How do we discover the closed form of G inversed? Some of you may have read through the module already, and that would be great. Okay, I really appreciate people who read ahead of time. Because when they do ask questions, those questions tend to be a little bit more specific, which makes it easier for me to answer those questions. But for people who have not read through the notes, I'm just going to explain the rationale of how how I went about to derive G inversed as a function. All right, so everything starts with observation, and then from observation we perform abstraction. That is the whole idea of programming, because even with the simplest kind of programming, which is kind of a macro, for those of you who don't know what macro we are referring to, I'm just referring to certain things that we do repetitively, let's say in Excel. And the simpler thing that to do quote-unquote programming is to turn those into macros, which is basically just to do this and then do this and then do this and then do this, okay, with no condition statements, no loops whatsoever. But it is still a form of abstraction, because we are abstracting that particular sequence of operation into a single abstract description or single abstract action. So that's what programming is all about, and that's why this particular process that I'm going to show you may not be very useful on its own. On the other hand, I'm hoping that you guys might get something out of this discussion that is actually applicable to your future jobs as a software engineer, a computer scientist, or a developer. All right, so let's go ahead and start with the observation. The observation is actually done quite a few slides ago, so I'm going to go back to the slide where we can make an observation. So this is the slide where we can start to make an observation. And the observation has to do with we're filling in the numbers in a diagonal way. Okay, just like that. And given a particular number, the first thing we really want to know is which diagonal line is that number corresponding to. That probably is the first thing we want to do. So let me fast forward to the new page that is blank. Okay, so here's a blank page. So let's say we start with the number n, okay, and this is the two-dimensional space, and today I'm not even bothering to use a ruler. So we're starting with an n. We want to know, okay, so where's this, where's the pixel corresponding to the natural number n? Well, we know certain things about n, right? So we know n is, once we discover the coordinates, x and y, n is g of xy. So xy are the solutions. We don't really quite know how to get there, but we want to establish the relationship between n and xy first, and then we look at that and go like, okay, is there a quick and easy way for us to solve this? So g of xy, once we expand it based on, how g itself is defined, and we talked about that on Monday, is x plus y, the whole thing, times x plus y plus 1, the whole thing. Yeah, my penmanship is not really that great. And then the whole thing plus y. Okay, so there's no surprise here because this is how we derived g of xy on Monday. And you can see that there's a whole bunch of xy, and for the most part, except for this y out here, this xy here, we can just kind of combine xy and call it d. So we define a term d and say d is just by definition x plus y. And d stands for diagonal because we want to find out which diagonal line this pixel is supposed to belong to. So once we know, once we define, d, which is really just a shorthand, now we can rewrite, n to be something like this. So we have d times d plus 1, the whole thing divided by 2, and then we still have a plus y over here. So some people look at this and go like, that's not helping. I mean, we still have two unknowns, right? Because just by defining d to be x plus y does not remove an unknown term from the system of equations. However, it does make things a little bit easier to deal with because we know x and y are both natural numbers. So that means if I decide to get rid of y over here, I just have to change this equality into an potentially inequality because y can be 0. So now I can say, okay, maybe n, I can rewrite this whole thing as n is greater than or equal to, and this time I would put d squared divided by 2. I'm just, separating or distributing the terms right now. And then this is plus, let's see, d divided by 2. Yeah, so all right. So are there any questions about what I just did here? Going from the equality into the inequality because I removed the plus y at the end of this. Okay, I'm not seeing any questions in the text channel. Okay, makes logical sense. Very good. When I first glanced at the text channel, I thought I read magical sense. That might actually make sense too. Makes magical sense. But no, in this class, we don't want things to make magical sense. We want things to make logical sense. All right, so now we multiply both sides with 2, so now we have 2n is greater than or equal to d squared plus d, and now we can put all the terms to one side. So it's up to you to decide how you want to do this, but I'm just going to put the 2n on the other side. So we have d squared plus d, and then minus, subtract your 2n from it. All right. So at this point, we have a kind of strange thing going on, because if this was a equality, then we go like, oh, this is just quadratic equation. D is unknown, but n is known, because n is what we are given with, is the natural number corresponding to a cell. So n is known to begin with. We just have to figure out d, and if we have something like this, and this is actually a equality, then we can solve the equality using quadratic equation. Well, when it is an inequality and we still have 0 on the other side, we can still do it. We can still solve for the quadratic equation. It's just that of the two roots of the quadratic equation solutions, we'll just naturally pick the one that is smaller, because if we had picked the larger one, because if we pick one of the roots, it's going to guarantee a 0, but then we just have to say that d is less than, I think d has to be less than the smaller root, so that we can satisfy the inequality of this entire expression is less than or equal to 0. So that is the trick. Okay, that really is the most important trick of the entire derivation, is to turn it into an inequality by losing one of the unknowns, turn it into an inequality but still has the structure of a quadratic equation. Basically, instead of a quadratic equation, now we have a quadratic inequality. But it still gives us, the solutions. Basically, it will still give us, the value of d. And once we get to the value of d, we know what d is. D is x plus y. So now we just have to solve for, once we know d, we have to solve for y, which is pretty easy because we basically have to plug d into here, plug d into here, and we know what n is. So we just have to subtract this portion here from n, and then we get to y. That's the general idea. Now, I'm not going to go through the entire derivation on the tablet, okay? But I do want to show on the tablet is just the most important portion of the derivation. So now that we have done a good portion of the explaining of the derivation, which really is not something that I can ask in an exam. Simply because it's already done. I mean, what is to ask in that case? So the key is to turn it into an inequality, a quadratic inequality. We solve for w, but we know w is has to be a natural number, which means w cannot be negative. If we know w cannot be negative, then we know what to do with this plus or minus. We cannot do the subtraction. We have to do the addition. So we only pay attention to one of the roots of the inequality. And then furthermore, we also know that w is supposed to be a natural number because this inequality by itself without the floor is going to give us an irrational number most of the time. So we don't want an irrational number. We want a natural number. So we just take the floor of the irrational number so that we end up with a natural number. So some people may be asking, why do we take the floor instead of the ceiling? Well, the reason why we have to take the floor instead of the ceiling is because this entire expression is supposed to be less than or equal to 0. When w is the irrational number, the expression does equal to 0. So in order to make this entire expression on the left-hand side to be less than or equal to 0, we basically have to take the floor function of the irrational root that usually is the result of solving this particular formula over here. So once we know that, okay, this is basically just going back to what I said a little bit earlier. We plug in w instead of x plus y, and then now we can solve for y. And once we solve for y, x is easy because x plus y equals to w. I just use a different character variable in this case because w is x plus y, and once we know y, x is really easy to figure out because it's just w minus y. So that's how we solve for both of the numbers as a coordinate. So to summarize, okay, let's define w of n to be this thing, which is basically just this thing here, except I parameterize it. Instead of just saying w relies on n, I make w a function of n. So that makes it very easy to tell what is the independent variable and what is the value that we are trying to compute based on the independent variable n in this case. And once we have this notation, we just have to plug it into this one here as well as this one here. So now, when we are given a natural number, we just have to apply w of n just like this in order to figure out the first portion. This portion here is the x portion of the coordinate, and then the second part is the y coordinate. And that's basically it. So now we have G, which is the one that folds the space. So we can start with a two-dimensional space and end up with a single-dimensional space. But given that we have just a natural number that is corresponding to how we do the tiling, diagonally, we can now figure out which tile ends up with that number in the two-dimensional space as well. And that is the job of the G inverse function. So do we have any questions? Okay, I think someone's mic is, doing certain things that might be on. So your mic is not muted, so it might be yours. Okay, that's good. Thank you. All right. So do we have any questions about this portion of the Aleph null module. I'm not sure how many of you actually read through the reasoning of how to derive G in closed form and how to derive G inversed in closed form, because it really is just a bunch of math, and none of this math is beyond your reach. Given that you have all taken not CIS, Math 370 and Math 372 or the equivalent, you have enough math background not only to understand this, but given enough time and mostly motivation, you can probably do this derivation as well. What is the closed form? Right here. And it does depend on Wn, but Wn is defined here. Oh, closed form means we are not using sigma, we are not trying to use a loop to test things. It is just using existing mathematical operators. That's basically what closed form means. Anytime you see a sigma, that is not closed form. When you see the integral symbol, it is not a closed form, because it requires if all is okay, this function is the integration of this function, integral of f of x dx, and until you solve it into a closed form, in order to get the actual answer, you actually have to go through some kind of loop or numerical analysis. But once you have the closed form, then you can just apply known mathematical functions and actually get the result without having that special logic to have to go through. All right. All right, so any other questions related to the Aleph null module? Okay. So let me pose a question then. So I'm going to pose this question of, since we have a way to fold 2D into 1D, two-dimensional space into one-dimensional space, what about three-dimensional space? Or four-dimensional space, five-dimensional space? Do you think those also have the same cardinality as just natural numbers? All right, so Jonathan is correct. It is possible because all you have to do is to apply G in a nested way. All right, so let me switch back to the tablet because this is probably easier for me to just write out in the tablet rather than typing it out. So let's just say that you have a three-dimensional space. So you have n times n times n, and you want to map it to n, or you want to see whether it's possible or not to map it to n. So let's call this function h, not to be confused with g that we have already derived. So if I just say that okay, I just need a bijective function h that can do this, I don't really care how you get it done. I just need a bijective function. So how do we do it? Yes, so Aman is correct that 3D is like infinite 2D slices, but how do we utilize how do we do this in the laziest possible way? I think that's what I'm trying to ask, is how do we do it in the laziest possible way without having to reinvent the whole thing? Because if you think about it, okay, you can look at a 3D space, okay, so here's my approximation of a 3D space. And what you can do is to apply the tiling thing, except this time we're not tiling, we are basically stacking cubes. So we stack a cube at a corner, and then we stack a cube right next to this corner, next to this corner, next to this corner here. So we basically apply what we have learned, except we are doing it in a three-dimensional method. The other way to look at this is to look at the three-dimensional space, kind of like turn it so that the the corner is pointing down, and then you're kind of like it's just like pouring water into that into that cavity, and the surface that you're filling each time is going to be a triangle, and we can use about the same scheme that we have used to fill up diagonal lines, except this time it's not going to be a diagonal line. It is going to be a triangular surface that you're going to be filling up with quote unquote water, except it's not water, those are all tiny little cubes. So you can do it that way. But that's not easy because we have to rederive all the equations, right? So nah. Okay, so we want to do it using the easiest possible way. So I can now say, okay, let's give me a three-dimensional coordinate x, y, and z, and I am just going to turn it into a single natural number by applying g twice. So I can apply g, okay, so don't copy it yet. So I'll apply g to xy first, and then I'll apply the result of gxy and combine that with z and apply g one more time. Because I know that this is going to give me a natural number, right? And z itself is going to be a natural number, so I can easily just nest the way I apply g to come up with h over here. So this way I don't have to reinvent the wheel just by going like, oh, so instead of filling diagonal lines, I'm now filling triangular planes, and the way we do counting is completely different, and now we no, none of that. Okay, because what we can do is really just to apply g in a nested fashion. All right, any questions? So it looks like Armand has a point or question. So one interesting thing about this, okay, even though it is not a very practical thing to do, very good. Okay, so Armand asked a very good question. So, and I didn't really quite touch on the topic of compound functions. So a compound function has a special notation. So if you look at h, now this h has nothing to do with the h of the previous slide, nor does f and g. So I'm really just using h. F, G, and H in a different way on this particular page. So if I define h of x to be let's see here, to be h, to be nope. Okay, let me take it back. To be g, h, f, sorry. Okay, of x. If this is how I define h, so I need to have defined f and g already in order to say that, oh, h of x is really the same thing as first applying f of x, whatever that returns, apply g on top of that. Okay, so this is basically a compound function. And the way we write this compound function is f and then little circle here, g so h is defined to be the compound function of applying f first and then g. So I'm not sure how many of you are familiar with this notation. You can type in the text channel if you have some exposure to this particular notation, or you can just go like, nope, have never seen it. Okay, some people might have seen it. If you have taken some of the more advanced calculus classes, you probably have seen this, because this is how you do derivative when you have a complex function. Calc 1, there we go. Thank you. So if you haven't seen it, it's okay. It's not a problem. Okay, so I'm going to give you a theorem without proving it. Okay, so I'm going to say that if f and g are bijective, then h is bijective. Okay, so that's what I'm going to use to prove my point, that the nested application of g is going to be bijective. So let's get back to this statement here. Okay, and once again, we do not have the vocabulary to do this proof yet. Okay, but if you think about it, does that make sense? Okay, because now most of the other textbooks would give you a function as a map from the domain into the codomain. So if f is bijective and g is also bijective, so what that means is I have one element here that will map to one and only one unique element over here. Each element in here is going to be mapped to one and only one unique element over here. So it sort of makes sense. Now I'm using the word sort of because this is not a rigorous formal proof, but it sort of makes sense that so that means this thing here that started all the way this thing here that started all the way in the original domain is going to map to one and only one unique thing all the way over here in the final codomain. Sorry, my phone is ringing. Let me see if I can. There we go. Alright, so it sort of makes sense that we can argue that when you combine f and g, we end up with another bijective function to go straight to here. So sort of makes sense, right? So once again, I want to give you a heads up of how we can potentially prove something like this. I believe proof by contradiction is going to be very helpful. In other words, we basically say, yes, given that f is bijective, given g is also bijective, let's say h is not bijective. Now, there are only two ways for a function not to be bijective. It may not be injective, it may not be surjective, and then all we need to show is nope, it is not possible for h to be not injective, and it is also not possible for h to be not surjective, and as a result, h has to be bijective as well, given that f and g are bijective. So I'm not doing a formal proof right now because we have not talked about proof by contradiction, but this is the general idea of how I think this theorem can be proven. Alright, so we got a text message coming in. I'm going to pause a little bit here to basically address that first. We got two. Alright. So with this line of it's obvious thinking, you could apply the theorem to surjection and injection because it makes sense going from f to g. The cardinality of y does not equal to the cardinality of x can be used to contradict. Yes. So when we have a bijective function, the domain and the codomain must have exactly the same number of elements. Or, yeah, so they must have the same number of elements, or they have to be, even if they're infinite, they would have to be out of null. They have to have the same cardinality. So given that, so that means this set here has the same cardinality as this one here. This one has the same cardinality as this one here. But all that is establishing is we know that the cardinality of what we start with here has the same cardinality as what we end up here. Now just because where you start off with and where you end up with have the same cardinality does not guarantee bijection itself, but it does guarantee one thing. If it is injective already, it is guaranteed to be surjective as well, and vice versa. And you can also say that if it's not injective, it is also guaranteed not to be not surjective. So that means we only have to show that it is not possible for h to be injective, and that automatically shows that h also cannot be not surjective. If it's not one, if it's not possible to be not one, then it is not possible to be not the other one also. So we can, what Jonathan suggested, can be a shortcut to the actual proof, but we cannot rely on cardinality alone to determine whether a function is bijective or not. All right. So when we get to the proof concept, we're going to come back. I hope so. I remember to do this, and if I don't, you guys can remember to remind me to do this because these are very interesting applications of those specific proof techniques. Very good. I like where this discussion is going. It really means that you guys are really thinking about this. You're absorbing the content and processing it and actually take it to the next level. That's good. All right. Any more questions? Any more points you guys want to make about this particular module? All right. I'm not seeing anything in the text channel. Cool. All right. So let's move on then. And now we're going to talk about the next topic. So the next topic is not aggregated score of exam 1. Now we do have practice exam 1 coming up on next Monday, which means the actual exam 1 is going to be the Monday after next Monday. All right, so we have about close to 2 weeks. We have basically 12 days before the first exam takes place. The first exam, all the exams is going to take place. Exam 1 and 2 will use the entire lecture time. So basically, you just have to show up, quote unquote, show up, and I will distribute the test. I will tell you guys more details about it on next Monday of how it is going to be administered. It's going to be 12 days from today. Today is the 15th, so plus 12, that will make it the 27th of September. Yep, it's going to be September 27th. Oh, okay. All right. So so next Monday, we are going to do a practice test, and if you guys can help to remind me, I can send out the practice test ahead of time so that you guys can actually start to work on it before I talk about the solution of the practice exam. All right, so relations is out of the scope of exam 1. So exam 1 is going to have only the material up to and including Aleph Null. Relations is not included in exam 1. I just want to make it very clear because I don't think we'll have enough time to do assignment with relations by the time we get to the actual exam date of exam 1. So that's why I'm excluding relations from exam 1. It's going to be for exam 2. All right, so getting to relations. There we go. So we'll start with what is a relation. A relation technically is basically whether two elements of a set are related or not. Okay, so let me highlight the sentence that I'm reading. Okay, so that doesn't really tell you a whole lot, does it? Right? Because a relation is telling you whether two elements of a set are related or not. That's really circular. Well, that's kind of what it is also, because what relation are we talking about? It can be anything. Okay, you can define relations in any arbitrary way that you wish to, as long as it makes sense for whatever application you use the relation for. Now, later on, we're going to talk about some actual useful relations, and I can give you a preview ahead of time too. Less than is a relation. So given two integers or given two natural numbers, the relation is one less than the other one. That's a relation. Equal to is a relation. Not equal to is a relation. Yes, we are taking roll, just not yet. I got everything timed, so so it's not time to do it just yet. I know Jonathan really just want to get it over with, but it's not time to do it yet. So we're gonna wait a little bit. Yes, well, it's good. Okay, you guys are paying attention, so that's good. So so one thing we know about relations, so if R is a relation, the only thing we know is it is a subset of the Cartesian product between x and x. And someone looking at this may say, oh, that's about the same as a function. Well, actually, it is not the same as a function, because a function has a domain and a codomain, and the domain and the codomain do not need to be the same. In the case of a relation, they need to be the same. In other words, a relation is relating elements within the same set. It cannot relate an element from one set to elements of another different set. So that is really important to understand. This is the first difference between a function and a relation. Now, someone may be asking, but I can certainly use the same set as the domain and the codomain, right? There's no rule against it. I mean, in fact, you can quite easily define identity functions that just maps an element to itself. Then you can use the same set for the domain as well as the codomain. Yeah, there's no rule against it. So there are certain subsets, okay, of these things that can also be functions. Okay, that there's a certain overlap. Okay, there's a certain overlap between relations and functions, but generally speaking, they are not necessarily the same thing, and they're used for different purposes. So I just want to make that very clear. All right, so there's a question in the text channel. So R is related to set X, or R is related to the elements of set X. So R is basically just a subset of the Cartesian product between x and x. So what R does is it relates an element potentially of x to an element of x. That's all it does. It is just relating elements of x to elements of x. I hope that helps to clarify Jonathan's question. So R is basically defined, it's said that R is a relation defined over X in this particular case. So R isn't something that is being compared here. That is correct. R is not being compared. Okay, so maybe I can use an example to illustrate what a relation is. And then I can show you what a relation is not, okay? So let me see what is the best way to do it. I'm going to try to use a mind map to do this part here. Okay, so we are getting into relations, so that's good. So we'll go ahead and just pick a particular x here. So we're going to say x is, we'll just have a, b, and c, okay? So that's all we're going to do is to define set x to be a, b, and c. And then Jonathan typed in the text channel, so R isn't something that is being compared here. That is correct. So we are simply relating, the elements of X. R itself is a subset of the Cartesian product. So in this case, we can use an example. Okay, so there are many R that we can define here. So I'm just picking this particular R and go like, okay, so it has AA, BA, and CB. Okay, that's all. Alright, so in this particular case, R is a relation defined over X because it is definitely a subset of X Cartesian product with itself. Now, it is just a subset, and don't ask me why A relates to itself, B relates to A, and C relates to B, because that is completely arbitrary. Okay? But this looks like a function, right? Because if I say R is also a function with x as the domain and x as the codomain, yeah, you can definitely say that too. So now I'm going to change this a little bit so that it is no longer a function, but it is still a relation because it is still a subset. Because all I can do, there are several ways to make this, but I can just add one more thing, and I'll just say that, by the way, A also relates to C. Now, it cannot be a function, right? This R cannot be a function with x being both the domain and the codomain, because A is mapping to two different elements in the codomain, because A maps to A also maps to C. So it cannot be a function in this case, but it's still a relation, because in order to be a relation, all it needs to be is a subset of the Cartesian product of the set the relation is defined over and itself. So I'm hoping this helps to illustrate. So I'm going to make a very clear point here and say that this is actually also a subset equal to the Cartesian product of x and itself. There we go. So this should make it kind of extra clear, that R is indeed a relation defined over X. So are we good here, or do we have any questions about what is a relation? This is a relation. It's just kind of arbitrary. All right. Okay, so let me give you another example. Okay, so let me give you another example. So this time I'm going to pick y as the set of with elements to be related by the relation. So we're going to have defined y to be so this time we do have values that are comparable, because we can tell that 1 is less than 2, 2 is less than 3, and so on. Okay, so this is just arbitrary. Okay, I'm defining y to be like this, and now I can define s, as a relation. But this time I'm going to define s to be a relation that actually has some meaning. Okay, so I'm going to say I relate 1 to 2, I relate 2 to 3, I relate 1 to 3. Now remember, all of these here, these are tuples, which means 2, 1, and 1, 2 are considered distinct. Okay, they're considered to be different. So now I have this relation S that is defined over Y. 1 it relates to 2, 2 relates to 3, 1 relates to 3. So instead of calling this set S, okay, instead of calling this relation S, I probably can just define it to be less than. In other words, this is not less than or equal to. This is basically using the less than symbol as the funky name of a relation that is defined in this case to have these 3 elements in that particular set, and as a result it is relating 1 to 2, 2 to 3, and 1 to 3. So in this case, this is, okay, given that y only has the values 1, 2, and 3, 1, 2, and 3, this is indeed the less than relation that can be defined over y using the typical usual numerical sense. So are we still doing okay so far with the concept of a relation? It's much more general and flexible in a way compared to a function, because there's no such thing as, oh, one thing from the domain can only map to one and only one thing in the codomain. Nope, there's no restrictions like that. Okay, so in this case I can also define another R, okay, that is also considered a valid relation that is defined over X. Okay, and you guys look at this and go like, wow, okay, now I have seen everything. This R here, okay, instead of define R like this, if I define R to be an empty set, that's perfectly okay. That is still considered a relation defined over X because it just has to be a subset of the Cartesian product of X with itself. An empty set is a subset of every set, including itself, so there's no problem of defining a relation to be just an empty set. So I noticed that a few people are typing in the text channel, so I'm going to pause here and see what questions are coming up. Alright, so the first question or first point is, these just seem more like observations of elements trend rather than a rigid function when considering the special properties. Well, we haven't really gotten to the quote-unquote properties or characteristics of certain relations, but in general, if you just want a relation, it just has to be a subset of the Cartesian product. And then on is asking, is less than a less than relation? Yes, it is. So if you want to define greater than, it's easy. Okay, using the usual numerical sense to define greater than is easy. So greater than is defined to be the following set. You just have to flip everything the other way around, right? 2 is greater than 1, 3 is greater than 1, and 3 is greater than 2. And now we have a relation that is greater than, but this is defined over the original y. it only makes sense when you say, this is how we look at greater than over the original set of y. What makes it less than and greater than? 1 is less than 2, 2 is less than 3, 1 is less than 3, 2 is greater than 1, 3 is greater than 1, 3 is greater than 2. It's really just spelling out, how everything in y potentially relate to other things in y. Okay? This is just an example. It really is just a very simple example of how you can utilize, how we normally understand less than and greater than, and use those as relations and define those relations over a finite set in this case. That makes it very easy to see things because if you're working with a set of all integers, it's kind of hard to see every single possible way for the elements to relate because it's an infinite number of elements. On the other hand, once we are looking at something that is a finite set, then it becomes a whole lot easier to use examples. All right. Because this is less than does not include equal to. This equal is basically saying I'm using a very funky name for a relation. I'm using the less than symbol as the name of the relation. That's why. Yeah, so if you don't like this, you can just replace the less than symbol with L, and then replace the greater than symbol with G. That makes it very clear that that L and G are just set of two tuples that turn out to be subsets of Y Cartesian product with itself. So yes, the notation can kind of get in the way here. All right. So I'm gonna make you guys even more confused here. Apparently I'm very good at this without even trying. So I'm gonna do it here. So I'm gonna define LE, which is less than or equal to. And if we want less than or equal to as a relation, and we want this relation to be defined over y again, now this time it is a little bit bigger because 1 is less than or equal to 1, 1 is less than or equal to 2, 1 is less than or equal to 3, and then 2 is less than or equal to 2, 2 is less than or equal to 3, and then 3 is less than or equal to 3. So this is a much larger subset in order to capture less than or equal to. Does that make sense? Because I think now it makes more sense because less than or equal to is the name of the relation. This equal here is simply saying this is the name of the set. It is defined as such. Yep. Okay, cool. Okay, my alarm clock just buzzed me, so it's time to take a roll. Yay. Alright, so let's go ahead and take a look at the roll taking activity. Alright, so is this one? Yes. Cool. And I'll show you the answer first, and then I'll release it. Alright, so the roll taking word is macros. So lowercase macros or uppercase macros. That's the name, that's the actual name of the spaceship that I talked about yesterday. SDF1 is kind of like the numerical designation of the super dimension fortress, but the actual name is Macros. And I set the time to 5:32, so you have approximately like 8 minutes to do this. I mean, that's actually plenty of time. It is not plenty of time for people who are not present in the class. But for people like you who are watching this, live and synchronously, 8 minutes is plenty of time to copy and paste macros into the editor box. And Macross is also the name of the series, the Japanese anime series. It has very good. The one thing that set Macross apart from Gundam is Gundam comes with crappy music, just crappy. And Macross has some of the best soundtrack, in a Japanese anime. Yes, I digressed. I think with Gundam, there's a little bit more political things, going on. That's always going to be a Gundam thing. Doesn't matter whether you're watching Gundam Wing or Gundam, any Gundam series always has a very heavy-duty political uh, aspect to it. I think the later Gundams do, but the original Gundam, didn't come with very good music. The mecha design, at the time, was actually quite good. All right. So I got the main concept discussed, a concrete example, and a random example. Okay, so the random example is kind of useful because it talks about certain notations. So if this is R and this is X, we can say that R is a relation defined over X, okay, because it relates elements of X to other elements of X, potentially also the same element. So in this case, what we can do is to look at the notation. If you want to say A and B are related, through R, you can say ARB, because we can see that AB is a two-tuple of R, and R is a relation defined over X. So ARB by itself, can be used as a notation to ask whether A and B are related via R. But you can also say whether a particular two-tuple is an element of R or not. So you can say, oh, BC is a two-tuple that is actually in R, which basically is also saying the same thing as BRC is true. BRB is false because you can see that B does not relate to itself as defined of R, so BRB as a Boolean expression is false, but you can also look at it from the perspective of whether a two-tuple is an element of R or not. So in this case, DC is not one of the elements of R, which also means D does not relate to C via R. So let me look at the text channel. A and B are just elements. That is, they are elements of X. Yes, they are elements of the set where the relation is defined over. Okay, and Armand says, thinking more mathematically, considering integer functions, x squared plus y squared equals to 1 wouldn't be a function but could be a relation. I suppose you can. Well, it depends on the types of x and y, because in this case, if we confine ourselves to just natural numbers, then we cannot find a pair of x y to satisfy this constraint. So in your case, okay, with Armand's example, we are looking at pairs of x y, so that by choosing those specific values of x and y, it satisfies the constraint, which is x squared plus y squared. It has to be 1. But that's a very you can look at it as a function. Okay, you can use this to relate x y. Okay, you can look at it as a function, but it is very restrictive as a function in that case. All right, so at this point, it's before we get to special properties of relations, it's probably a good idea to kind of talk about what is this stuff useful for, because it looks really kind of arbitrary and doesn't seem to be very useful. So I'll give you an example. It has to do with whether things can be sorted or not. And most people are thinking like, what do you mean by whether things can be sorted or not? I have taken some classes and we talked about sorting algorithms and so on and so forth. So are you telling me that certain things cannot be sorted? And the answer is yes. Okay. So you have to be very careful when you think about, can I sort things within a particular array? I'll give you an example. Okay, so let's just say that you are hired by a gaming company, And every week, you guys will have to evaluate and find the gamer of the week. Now, I choose, gaming because I know this will wake up certain people in the class and goes, the moment I mention the word game, they go like, what? What are you going to talk about? So you're working for a gaming company, and every week you have to find a way to select the gamer of the week. So this is obviously a comparison kind of thing because you want to choose one person who is more gamer than all the other gamers, right? Now, how do you define that? How do you define that a person, one particular gamer, is more gamer than other gamers? So there are a lot of things, right? Okay, so there are a lot of things you can use to evaluate that. You can ask, okay, what is the win-lose ratio of this person? Cumulative or just over the past week? Okay, that's one. Two, how many teammates of this particular gamer, say this is a great person to play with, not salty at all, helpful, encouraging, and all that good stuff. That's another evaluation criteria, right? So, and then you can also, depending on how the game is run, okay, for certain types of game that really wants you a lot of money, you can also look at in-game purchase, okay? How much money this dude spend, in this week, okay? The more money you spend, the more gamer this person is. So you can see how you can end up with a lot of metrics, okay? A lot of numbers that will eventually be useful to evaluate whether a person, how a gamer compared to another gamer. Now, when you look at this relation, when you look at gamer A and gamer B, okay, so think of yourself writing a C function, okay. A is a structure representing a gamer, B is a structure representing another gamer, and it has tons and tons of attributes, okay. And you're trying to define whether A is more of a gamer than B. So if you're not careful, you can end up with a situation where things are not entirely comparable. So what we say here is it is not I have to remember what the term is. Partially ordered versus totally ordered. So you can sometimes you can end up defining a relation that is only partially ordered instead of totally ordered. So when you have a partially ordered relation, you can't really select just one single gamer of the week because certain gamers cannot be compared to other gamers. It doesn't have that relation defined. So this is why it is kind of important to understand all this stuff here, because if you want to run a sorting algorithm, the comparison operator that you define, over whatever you're sorting, needs to be totally ordered. And if it is something simple, like a less than for integers or real numbers, it's not a problem, okay? Those things are known to be totally ordered. On the other hand, if you are defining your own comparison operator, because you have to combine many attributes and different, really complex logic, it is entirely possible that you can end up defining something that is only partially ordered and not totally ordered. And when you try to apply a partially ordered comparison function to a normal sorting algorithm, it will give you a result, but that result may not actually be correct. Okay, it's not going to be useful in many cases. So this is the pragmatic reason why we talk about relations. So how do we define something is being partially ordered versus totally ordered? That relies on this bunch of stuff that we are going to talk about. So we talk about whether a relation is reflexive, whether a relation is symmetric, whether a relation is transitive, whether a relation is anti-symmetric, and then we can start to define whether something is partially ordered or not. So I'm just giving you the context of why this stuff is kind of important to understand, because a lot of times people don't think about this and they go like, yeah, I'm a gamer myself, I know how to evaluate gamers, but that person lacking the knowledge of what we are talking about here, may end up defining a function, a comparison operator that is not totally ordered. And what's going to happen is the whole bunch of gamers would get really upset because hey, this ordering is totally bogus, and they may end up leaving the game, or they may complain, and bad things may happen. Yes, I know it's far-fetched here, but as I said, I have to keep you guys in the context of gaming just so that certain people stay awake, during this lecture. I have a special talent of putting people to sleep. So another digression. It won't take long. A colleague of mine lost her husband about I think about 2 to 3 years ago. Very sad. And she couldn't sleep, okay, because that was her husband for I think 40 years. Um, and she told me that she eventually started to watch my lecture recordings, because she couldn't watch anything that is like really boring, like monks, humming or stuff like that. That's too boring. But she cannot watch anything that is too exciting either. So as it turned out, my lectures is exactly right where that narrow band of things that seem to be interesting but really not very interesting. So she said she for the first time in weeks she was able to sleep really well just by watching my videos. Yeah, so so anyway, that's kind of interesting. So reflexive, okay? So how do we know, a particular relation R that is defined over a set X is reflexive or not? We evaluate this particular quantified expression. So this quantified expression is actually pretty simple, right? Because all it says is, let's look at every element of X and just make sure that EE is an element of R. So in other words, we just want to make sure that every element of X relate to itself. That's all. So it seems simple, right? So let me give you some examples. Just because it looks simple doesn't mean it is. So I'm going to give you some examples. This time I'm going to use mouse pad because this stuff here I can just type it pretty quickly on the keyboard. So I'm going to define X, the set that contains all the elements that we need to relate. We'll just define it to be A, B, and C. Okay. So and then this time we'll define R. So what about R being an empty set? Do you think the empty set relation defined over X is reflexive or not? The answer is no. Very good. Because if when we evaluate, AA, let's substitute, let's bind. Okay, I have to use the right word. Let's bind variable E to element A, and the question now is AA an element of R? No, because R is an empty set. It has no elements whatsoever. So that means AA is in R is false. Well, because we are using the universal quantifier, so if this expression here is false for just one of the many elements of X, that makes the universally quantified expression false. So if this is R, then this R is not reflexive. Okay, and this is an easy one. Okay, we definitely understand this one. The next one is going to be easy too, and you guys will go like, yeah, so what is the big deal? What about this one? What if I define R to be AA as a 2-tuple, BB as a 2-tuple, CC as a 2-tuple, and it is defined over X, which only has elements A, B, and C? So in this case, yeah, this is reflexive. Okay, this is reflexive. And let me be grammatically correct here. This one is not reflexive. Okay, fine. What about this one? Okay, so I'm going to throw in something like this, and then throw in AB, throw in BB, throw in CC. Just for the sake of it, I'll throw in CB. So the question is this reflexive or not? So this is basically testing whether you can understand the universally quantified statement correctly or not. All right, you guys are getting it. Very good. Okay, this is also reflexive. Now, for potentially some people who are questioning, go like, but what about the extra stuff A, B, and CB over here? Doesn't that kind of mess up, this relation, so it's not reflexive anymore? No, it does not, because all this is saying is I need to make sure that A, B, B, C, C are in R. It doesn't say anything about um, two tuples that does not fit the pattern of EE. In other words, if you just give me everything, if we can just make sure that every element relate to itself, we can have extra things. It doesn't hurt. Okay, that particular relation is still reflexive. Okay, so that's really kind of important to understand that this is actually just saying the minimum that it takes for a relation to be reflexive, but you can certainly throw in extra stuff into R, and that R would still continue to be reflexive. Because that is not true for some of the other ones. Actually, most of the other ones can be harmed by throwing extra stuff into a set, into a relation. So let's look at symmetric. Let me first make sure that we don't have any additional questions about reflexive first, and then we'll move on to symmetric. So if you have any questions or any points you want to make about reflexive, now is a good time. All right, I'm not seeing any questions. Let's move on to symmetric. So for symmetric, this is the universally quantified expression that needs to be true in order for R that is defined over X to be considered symmetric. So let's read the universally quantified statement first, and then we'll go ahead and look at some examples. So for all E and F in X, well, that basically means the comma is basically just saying, E is from X, F is also from X. So if I were to, okay, let me go back to my map here. Okay, so because I want to use the mathematical notation here. So basically, the whole idea of for all A, B in X, P of AB is really the same thing as saying, the long way of saying this is for all A in X, open paren, for all A in, for all B, for all B also in X, and then open paren, P of AB. Close. Let me see how many I'm supposed to close here. One more, and there's one more. There we go. All right, so it's basically a shorthand. So if I say for all A comma B in X, blah blah blah, that really is saying for all A in X, and then nesting for all B in X, P of AB. So basically, it's just saying, just pick something in X to be A, pick something in X to be B, and they can be the same thing. They may not be the same, but just pick something. And then we just want to make sure that the predicate AB to be true. So that's basically what it is. Correct. The order is not really important. So if you flip B and A, we'll be flipping B and A over here. It still boils down to every way to choose two things from X, and those two things can be the same thing. Chosen from X. So we have two variables that can bind to exactly the same value in X. Is that okay? Or if you have any further questions about the notation, now is a good time to ask to clarify those things first. Okay, I'm seeing something coming in, so let me just make sure that that is addressed before we move on. Okay. All right, so now we look at the actual universally quantified statement. It basically, so the outer portion is just saying, okay, E and F are two variables, and each one needs to bind to an element of X. Okay, that's all the quantified statement is saying. And it's universally quantified, which means if I can choose one way for E and F such that whatever is inside is false, then the universally quantified statement itself is going to be false. So now the focus is inside here. So the inside is saying E and F being a two-tuple that is an element of R, if and only if Fe is an element of R. Okay, so this relies you to remember what is if and only if. Okay, this symbol here is if and only if, which is also known as, is equivalent to. So I'll give you a quick review of what it is. It basically needs both sides of the operator to be the same in order for the operator to return true. So if one side is true, the other side is false, then the if and only if is false. If one side is false, the other side is true, it will also give you false. If both sides are true, then it will give you true. If both sides are false, it will also give you true. In other words, it's just basically saying, is the Boolean value on the left-hand side the same as the Boolean value on the right-hand side? If you want to look at it in a very simplified way, that is basically what it's asking. So, let's go ahead and look at some examples. All right. So we are going to go back and look at this one here. Okay, so we are reusing the empty set, and we're asking, is the empty set symmetric? When X is defined to be A, B, C, and the relation is an empty relation, is an empty relation symmetric? So Jonathan has an answer. And I mean, the rest of the class, you don't have to type your answer, but it's probably a good idea to think about it and, basically just apply your reasoning to come up with what you think is the answer. Right or wrong, doesn't matter. I'm not grading this, okay? And Jonathan is correct. Jonathan is ahead of me, explaining why it is indeed symmetric. Okay? And the reason is R being an empty set means nothing relates to anything else, right? So no matter how you choose the E and F, this is element of is going to be false. And so is this one. Now, so you always end up, no matter how you choose, okay, no matter how you bind elements of X to the variables E and F, the left-hand side is going to be false. The right-hand side is going to be false. So now you have false if and only if false, and that is actually true. So that is why an empty relation is always symmetric. Doesn't matter what X is, it is always symmetric. So that's kind of tricky. Let's look at the second one, okay? So if I have X being A, B, and C, and R is AA, BB, and CC, is that relation defined over X, is it symmetric or not? Yep, that's right. It is symmetric. Very good. Okay, this is indeed symmetric. What about this one over here, the last one? It has AA, BB, CC, just like the one above it, but it also has AB and CB. Is it symmetric? It is not symmetric, and if something is not symmetric, you should be able to explain it and say, oh, by the way, if we bind a certain element as E and a certain element of F, that will make this if and only if false. So you just have to give me one example of how you can do it. You can add BA as a two-tuple and BC as a two-tuple, or you can remove AB and remove CB in order to make it symmetric. But as it is right now, is not symmetric. All right. So very good. Now, if and only if is actually quite easy to understand because all it takes is to say, oh, both sides need to be the same. Okay, if one side is true, the other side has to be true. If one side is false, the other side also has to be false. So the next one is a little bit more complex because it doesn't make use of if and only if, it makes use of if, okay, or implies. So let's take a look at transitive. So we'll first take a look at the quantified statement, and then we'll go take a look at some examples. So this is probably going to be the last one that we talk about, and we'll talk about the most confusing one um, next Wednesday, because next Monday we're going to talk about the practice exam. So next Wednesday we'll talk about anti-symmetric. So transitive says, okay, take three things. Okay, we have three variables and bind each variable to an element that is found in X. Now, it is possible that you end up with exactly the same thing. That's possible. You can end up with different things. It doesn't matter. Okay. So what we need to be true is EF in R and FG in R implies EG is in R. Okay. So let's go take a look at the empty set first. So if I define an empty relation, is it transitive? So this time you have to remember what is implication. We just talked about if and only if. Implication is not I hate to use the word symmetric, but it's actually it's a little bit trickier. Okay, I'll just put it that way. It's a little bit trickier. Is the empty relation transitive? All right, so it is indeed. So Elijah is correct. An empty relation is indeed transitive. And the reason why it is transitive is actually quite easy. Okay, we will just borrow Jonathan's argument from before. Okay, if R is empty, that means finding the element EF is gonna fail. Finding the element FG is gonna fail. Doesn't matter how you choose the element to be E, F, and G. These two are guaranteed to fail because there's nothing in R. So that means false and false is going to be false, which means the left hand side of implication is guaranteed false. So every time you have the left hand side of an implication being false, the implication itself is true. So that means we automatically make sure that the empty relation is automatically transitive. Yeah. What about this one? Yeah, I know we're hitting a little overtime here, but I do want to kind of finish this because it's now is a good time to finish it. So what about the second one? AA, BB, CC, is it reflexive? We know it is reflexive, we know it is symmetric, but the question is it transitive? It is indeed. Okay, very good. It is indeed transitive. Okay, because if EF, and G are exactly the same thing, then we can definitely say, yeah, that's boring. AA is in R, and AA is in R. AA is also in R. So every time the left-hand side is true, the right-hand side is guaranteed to be true because they all have to be the same. Okay, that's pretty easy. The last one is this one here. So now we want to ask, is this one transitive or not? So this one is a little bit funny. So what about this one here? Okay, this one says this one has everything of the previous one, but it also has the extra things of AB and CB. Is it transitive? The answer is yes. This one is transitive too. Okay. So next time I will show you something that is not transitive, okay? Because so far we haven't seen anything that is not transitive. So I'll show you next Wednesday something that is not transitive. Which also means, because it's going to be a week from today that we'll come back and revisit this. It also means, basically means, you might want to read the notes and read a little bit ahead of me over the weekend so that you keep the engine warm, when it comes to the relations. Just a quick review, just to make sure that you're familiarized with the terminology, with the symbols, and so on and so forth, so that next Wednesday, when we get back to the same material, we can pick right up, okay, and start to talk about what is anti-symmetric. Okay, I will give you guys the practice test in just a little bit, so that you guys can practice on it. Other than that, I don't have anything else to add. Okay. All right. So if I don't see you again, now keep in mind that I still have office hours, on uh, Thursdays and Fridays. So if you do have any questions, if you want to clarify something, just come to my office hour, and I'll be more than happy to help clarify certain things. Over the weekend, you can ask questions. It's just that the turnaround time is a little bit longer. So, but if you don't have any questions, that's also okay. Have a nice weekend. I will see you guys on Monday, and we'll talk about the practice exam on Monday. All right, bye. So have a nice weekend. Stay safe, um, and I'll see you guys on Monday. Yep. Good evening. Go eat. Go get something to eat.